Welcome to the ET380 lecture on digital communication techniques. Okay, let's talk about data. Data refers to the information being communicated. Data is digital if it's from a digital source. Analog information must be converted to a digital form. The benefits of digital data, we have noise immunity, error detection and correction, and we could use digital signal processing, which we convert analog signals and use computer processing. So we could do analog processes digitally, being filtering, equalization, phase shifting, mixing, and other analog processes. Here we could transfer data serially from one, in this case flip-flop, to another one at each clock pulse. We could also transfer data parallel, where each bit is shifted directly across parallelly. Okay, so let's take a look at some basic serial data transmission techniques. We could use simplex, which is one direction. Something like this would be like cable TV, which comes from the broadcaster directly to your home and one way only. Half duplex would be like a walkie-talkie where you could talk or you could receive, but you can't do both at the same time. And full duplex would be like your cell phone where you could talk and receive all at the same time. We can multiplex data where we have several input streams and we can mix them together with some technique, send them over one line and demultiplex them at the other end and reconstitute our information. So digital signal processors are a modern way that we could take analog information and digitally modify it. So we have an analog signal, run it through an analog to digital converter, run it through our DSP, which we could do many things that we could do with analog circuits, but we could do it digitally, such as filtering, compression. Compression, we could reduce the number of bits like MPEG and other type techniques. Spectrum analysis, and we could do just about all analog techniques like phase shifting, equalization, signal averaging. So we could do that all with a computer once we digitize that analog signal. So our output, we could go ahead and make it definitely directly to analog or right out to digital. Now let's talk about data movement and shift registers. Here I'm showing a serial in, serial out, also known as SIPO, and we have different ways to move that data, and we could go ahead and serial shift in, then out, rotate right where we return it to the beginning, serial shift left, then out, and rotate left. Next shift register type is parallel in and parallel out, or PIPO, where we have the data go in and then we clock it out parallel. Here we have a serial in, parallel out, or SIPO, where we clock the data in serially and we could go ahead and control it to parallel out. Last type of shift register is a parallel in and serial out, where we clock the data in and then we could transfer it one bit at a time serially, also known as a PISO. Here I'm showing a IC shift register. 74164 is obsolete but still available, where we could do 8-bit serial in and do a parallel out. So we have to clock these in one bit at a time, and then we have to control and shift the data out parallel. Here's another shift register, 74165, which is an 8-bit parallel in or serial in and serial output. So we could clock the data in either parallel or one bit at a time serially, and then clock it out serial. Here's a shift register configuration called a ring counter, where we clock in a signal and then we rotate it and we feed it back into the same input so that the signal continues in the same direction and rotates continuously. Here's another shift register combination, which we call a Johnson counter. And what we're able to do is clock in a signal and then rotate it, but we put it back in. We feed it from the Q0, feed it back in, so that signal reverses continuously. So we have 4 up, in this case 4 down. In order for us to convert from analog to digital, we need an analog to digital converter. This circuit shows a 3-bit flash where we have information on a voltage divider, and once this analog voltage goes in, it compares between the input and our fixed ladder, and once it's selected by the comparator, it'll go into a encoder and then put out the binary output. This is the fastest of the analog to digital controllers because it is instantaneous. Once it reads it, it comes out. So this is the fastest of the converter. Here I'm showing a digital ramp analog to digital converter, and also known as a pipeline, and there are several different varieties of a similar type ADC. And we go ahead and we take our analog input and put it into comparator. We're clocking our counter here, which is counting from 0 to 256 or 255, and it is comparing to our digital to analog converter. Okay, so we're providing a stair-step voltage, analog voltage, and when those two match, we clock and we lock in our D latch, and it puts out the code. So we count, create a stair step. When our digital to analog converter provides the same voltage, the comparator trips and we latch in the output. This type of ADC is slower than the flash because we could potentially count all the way up to the maximum before we actually trip. So this one actually could take up to 256 steps in order to find that voltage. Here's a successive approximation DAC, and it's middle speed. And what happens is we have our comparator, and we step this at one time, and we go ahead and we compare the input voltage with our approximation. So in this case, we have a binary output, and first we do is we compare 5 volts to the input. If it is, then we set a bit. And next thing we do is we compare 2.5 to our input, and if it's correct, true, we set a bit. Then 1.25, 6.25, all the way down. So we're comparing the input to these values, and we're setting a bit wherever it does, and then it adds up the values, and then it gives us the output of the input. One of the newest types of analog to digital converters is our Sigma Delta. It's used for industrial measurements in voice and auto. It's extremely precise, has a wide dynamic range, low noise. It can be used as 18, 20, 22, and 24 bits. And like I say, it's used for CDs, DVDs, and MP3 players. So what happens, we have a signal comes into a differential amplifier that's subtracted from the feedback from a 1-bit DAC, goes to an integrator which averages that signal, goes to a comparator, which is the clock, and then it comes out as a digital or parallel serial output. Here I'm showing a digital analog converter where we take digital values and convert them to an analog. Here we have an op amp set up as a summing amp, and it is a binary weighted summing amp. These are all binary numbers when we put them in, with values of 1 to 8. And this, add them up. If we do a binary count, we're going to get a minus stair step of analog voltages. So whatever we put in as an analog, as a digital number, we could get an output of an analog value. Here's another digital analog converter, and this is called an R2R ladder DAC. And this one's used in manufactured devices because it's much easier to get two values of resistors R and 2R, and it provides the same type of stair step. We put in a binary number and go through and output as an analog value. Here's a newer type of digital analog converter. This is a switch capacitor DAC. And this one's also used inside of analog to digital converters. And what we do is have capacitors which add up to 2. And we have the switches here which are locking in the voltages and going through a comparator. This is another type of digital analog converter. This is a string DAC where we have equivalent resistors set up in a voltage divider circuit, and we have MOSFET switches that are controlled by a 3 to 8-bit decoder. So at 0, 0, this transistor is opened or closed, and we get 0 volts out. And each one of these, if I fire this guy would be 2, would put out this analog voltage at the output. And if I just put this one out, it'd be the analog voltage of 7. If all of these are on, we'd get close to 256 being the 8-bit number. This unit also, a similar one, would be using currents on this side so that you would have a DAC that was putting out currents. When we're talking about analog to digital converters, we need to talk about sampling. And sampling is the rate which the analog signal input is measured. The greater the sample rate, the finer the resolution of the digital signal. Nyquist sampling rate is twice the highest frequency of our input signal. Oversampling is sampling greater than the Nyquist rate. So the disadvantages of oversampling is higher cost, higher power consumption, and increased memory size, and an increased need for faster processing. Undersampling is anything less than the Nyquist rate.